So what should I do? Got it.
Yeah. Did it work? Okay.
Oh, okay. Thank you. Golden finger. So furthermore, let us take a look of the leading singularity of the Cauchy integral at kappa j, which is written explicitly here. It contains good property, however. So first, the first good property, important property, is the scaling invariant property. That is, if we dilate the polar coordinates by sigma tilde, then the leading the Cauchy integral so we compare these two integrals. So gamma tilde is invariant, and the Cauchy kernel is shifted, and the phase function could be under control. Now, oscillatory property. If you choose wisely the scaling parameter, then the oscillating property can be controlled. So this is the first good property. The second good property is the leading singularity can be integrated by Stokes theorem. So these are important. And so these are so to derive estimates for the lower order term, it is also important to know that natural spaces for the Hilbert transform to act on closely, because we are going, during the iteration procedure, we are going, the Cauchy integral will act recursively. So we need to know that for the Hilbert transform to act on closely, natural spaces are the Sobolev type spaces, WKB, and Holder continuous spaces. And for the Sobolev type spaces, usually involved with integration by parts techniques. They are used for the IST for 1+1 dimensional integrable system and the 2+1 dimensional integrable system if the background is a vacuum. Due to the singular structure of the continuous scattering data, we have to give up Sobolev type spaces because we cannot take derivative on this continuous scattering data already have 1 point. If you take derivative, then that's out of control. So based on this consideration, we finally choose the topology, the eigenfunction space, to be the set of eigenfunctions satisfying the following property. First, the reality condition. Then uniformly bounded at infinity. Blows up at Cn with bounded residue and the remainders. And in particular, the topology near kappa j, the eigenfunction, the topology of the eigenfunction near kappa j can be characterized by this property. Leading term are multivalued function. Precisely, they are sum of logarithmic functions in angle. And the remaining term are rescaled Holder continuous function. And we define the topology to be the sum of these norms. So So the rescaled Holder norm can be defined as follows. So first, that S and alpha be the polar coordinates. And capital Xj be the coefficients of Sj psi j alpha in the polar coordinate expression of the phase function. And the scaling, the rescaled Holder norm are defined by the scaling parameter sigma tilde, which are maximum of x1, square root x2, and cubic root x3. So the way we define remove the difficulty of oscillatory property difficulty, and also it respect the non-homogeneous behavior. So now I have some time, so I try to explain how to derive the estimates, prove the major estimates. So first, using the scaling property, and in terms of the rescaled polar coordinates, we write the Cauchy integral near kappa j, decompose it into sum of I1 up to I5. Indeed, difficulties occur deriving the Holder estimates occurred when the integral domain is a finite interval. To solve the difficulty, if R tilde is less than 1, we decompose the integral domain into compact parts and non-uniformly compact parts. That means if x tends to infinity, then this interval becomes larger and larger. And also, we need to decompose the integrand within the compact integral domain. Integrand are further divided into the non-oscillatory multi-valued leading term and the Holder continuous remaining terms. Estimates on the compact domain can be derived by using Stokes theorem and the Holder interior estimates if we decompose it in this way. For instance, to derive estimates, Holder estimates for I3, we need to decompose the difference in a smart way. Here, phi sub f stands for the product of the exponential wave function and f. So the first two terms, to estimate the first two terms, we use the special form of gamma tilde. Then apply the Stokes theorem, tell us it can be integrated. For the last two terms, remaining it depends on Holder interior estimates with a minor help from the Stokes theorem. So these are for the estimates on compact domain. For I4 and I5, the downside of our rescaled approach, because they are integrals on non-uniformly compact domain. And gamma tilde decays slowly at infinity. So to derive uniform L infinity estimates, we have to take advantage of the oscillatory factors, because gamma j behaves not so good. And efficient way to take advantage of the oscillatory factor is the deformation method, which depends on holomorphic property on S tilde. So in the remaining part of today's talk, to derive the estimates for I4 and I5, we shall always search for a deformation such that at the borders, the denominator is uniformly away from zero. And for the denominator, real part of the phase function is always non-positive during the deformation. And at borders up to sine k beta, the real parts of the phase function is bounded by negative constant coefficient monomials. So if we can achieve this property, the only problem is that we need to discuss the stationary point psi k beta equals to 0. So the deformation is, we will search out always like this form. So to this end, let us, I introduce this definition. First, homogeneous cases are defined by the xj axis. Degenerated non-homogeneous cases are defined by xi, xj planes. And fully non-homogeneous by the remaining ones. So we start with axis of homogeneous. The phase function is homogeneous and f is holomorphic. So the deformation for I4 is defined as follows. We deform real S to the complex plane. So if beta is positive, we deform real S to the lower half plane. If beta is negative, we deform real S tilde to the upper half plane. This implies that the real parts of the phase function is always non-positive during the deformation. And at borders, it is bounded by a negative constant coefficient monomial. So to control the denominator, we have to designate the range of the deformation angle so that at the borders, tau, the difference of Dagger with alpha minus beta is always uniformly away from 0. Thanks to the possibility, then using the positive, since S tilde and R tilde are both positive, so we have these estimates because the angle are uniformly at the boundary. They are uniformly they are apart. So we have these estimates. Then we use R. S tilde is bigger than 1, is larger than 1. We prove uniform boundings. The denominator is uniformly away from 0. So this is the deformation. So this is the picture illustrate the deformation for I4. So by applying residue theorem, interval 2, sigma tilde delta is deformed to the union of S less, gamma 4, and S greater. So we also use polar coordinates here. Now we deal with the stationary point. So by change of variables, the Jacobian only produce 1 over case root of psi k beta, which can be controlled if k is greater than 1, controlled by improper integrals. So for quadratic and or cubic k equals 2 or 3, then we can derive estimates. For I5, we use R tilde is greater than 1. Then the Holder estimates can be reduced to L infinitive estimates. So the same method, the same similar method, deformation method, can be used to derive estimates for I5, except that there could be extra contribution from the residues. And to prove, to derive the estimates for the iteration of the Cauchy integral for quadratic or cubic homogeneous cases, we also used adapt the deformation method we have, combining with Fubini's theorem. Also, we use the meromorphic property of the Cauchy kernel and the induction arguments. For linear case, the estimating are more involved. We have to deal with the stationary points psi beta equal to 0, the singularity. So indeed, we need a final decomposition of the integrand to squeeze out extra psi beta decay. Then the estimates can be go through. So I think I skipped it. So now we go to the degenerated non-homogeneous case. So we first have, I have to deal with them case by case. So first we have classification. For instance, case 1, 2 denote those cases so that in the phase function S3 vanishes, and the dominating coefficients in the phase function is x1. For each of them, there could exist extra non-trivial stationary point where the exponential function ceases to decay. So that means the deformation method will collapse there. However, if we compute the real parts of the phase function at psi j, where psi j are the polar coordinate, complex coordinate, polar coordinate centered at the critical point, stationary point, then we find their form is like this. So these are pretty similar to the homogeneous one if we do a proper decomposition of, so that is, first, we defined critical points on each ray fixed defined by a fixed beta, and on the ray, we define neighborhood uj sharp, which is shown here. So on the ray fixed by beta, S0 star and S1 star are critical points. So U0 sharp, U1 less sharp, and U1 greater sharp, they are intervals cut out by stationary point. That is, real parts of the phase function are semi-definite on them. So we similarly, we define deformation on uj sharp. And we can derive favorable estimates for the denominator And if we restrict to smaller neighborhoods of the critical point, we can derive, we can prove that real parts of the phase function is uniformly bounded by negative constant coefficient monomials if the dominating coefficients are not x1. So we derive estimates for I4. For I5, there are extra technical difficulty because if lambda tilde is close to the critical points, then the contour we choose near the critical point will be fixed on the real axis. Then difficulty, yes.
Just let you know you have about 5 minutes.
Yes. I finish this, then I stop. Okay, degenerated non-homogeneous. So the denominator will be, it's impossible to control it uniformly away from 0. However, R tilde larger is greater than 1, then the whole Cauchy kernel, the Cauchy kernel is no longer a singular integral here because we use R tilde is greater than 1. So Cauchy integral here is no longer a singular integral and can be controlled. So if for case 1,2 and case 1,3, you use the same deformation and derive favorable uniform estimates on U0, but near the critical points, you will discover that the coefficient will tend to 0 if x1 tends to infinity. Therefore, you need to do rescaled again because you rescale too much. Coefficients cannot, so you rescale again and derive favorable uniform estimates. And also you need to prove for this case, for degenerated non-homogeneous case, it is easy to see that the critical points is great in the new rescaled matrix is greater than 1. So the Cauchy integral there is no longer a singular integral, and we can achieve the estimates. So let me, I think I stop here. For the fully non-homogeneous cases, the computation is more involved, but ideas are the same. And luckily, they are only, you need only to study roots of second order polynomial. So it's still okay for higher, yeah. So let me stop here. Thank you.
Thank you, Derchyi. Are there any questions?
Can you say something more about the topology, the W space, like give a sense of how it compares to like a Sobolev space? Is this the norm is stronger or?
Okay, thank you. So for the W space, that's actually because we know the key is to derive the estimates near kappa J, and what is the estimates? Of course, is determined by W because they are just dual to each other. So after study the leading singularity of the Cauchy integral, then I divide the topology here. So actually A, so to your answer, A will be, no, B is actually the standard. If your background is a vacuum, then Witthuiser's results is just the eigenfunction is L infinitive. And for C, because the eigenfunction blows up, has a pole at Cn, So we know it is like the bone. Just since the Cauchy integral behaves well, they have symmetry cancellation property. So estimates for this is mild, except I make something. If you use the original subtle eigenfunction, then pores here is multiple. If you are multi-line, then estimates will be disastrous because you need to find a lot of cancellation, just like Boiti, Pampinelli, Pocketcop, they try to do this. But I think that's impossible. It's an ugly way to solve the inverse problem. So I resolved the difficulty by introduce more, by make the pore simple. Then the point is because this is intrinsic singularity, they are you need to study the Cauchy kernel property. But the Cauchy kernel, because singularity is caused by continuous scattering data, you cannot do integration by parts. So the only so you cannot, that means you cannot choose overlap type spaces like nonlinear Schrodinger, like KDB, like KP with vacuum background, like David Stewart, and you choose overlap type estimates. But for this, because continuous data has a pore, so the only choice, because singly, the only choice, you should turn to holder type space, because you solve that, you are working on Neumann iteration. They need to be close. So two types, overlap type or holder type. If overlap type fail, you try the other one. Try the other one, you need to solve the highly oscillatory property, which is killed by rescaled technique. Yeah.
Thank you.
That's the way.
Sec.
Yeah. My turn.
Thank you for a nice talk. I just had a maybe naive question or general question. If you approach KP2 through the complete integrability machinery, it's going to be a D-bar problem. Is this what you have when you have the Cauchy integral? Is this just coming from the D-bar derivative?
D-bar derivative? No, I don't think I understand your question. So, of course, I'm solving Cauchy integral equation via D-bar approach.
Right.
Because the data I choose is all of the data is non-holomorphic data, right?
Mm-hmm.
D-bar non-trivial and also multi-valued. They definitely represent D-bar non-trivial property.
So the C operator, that's the 2D Cauchy.
2D Cauchy,
Right.
that's the fundamentals
Right.
of it, because you take the data you choose is D-bar.
Yeah.
So you solve the inverse problem, the fundamental solution is Cauchy kernel.
So if we think of lax pairs, what you have in this operator is the D-bar
Next week.
derivative of the.
Next week, I will explain the
Okay.
Lex pair.
I'm not going to be there next week, so I was trying to make the connection.
Oh, I can talk to you. I can give you my slide.
Wonderful. Thank you.
Other questions? So I have one, which is now if you once you have the invertibility of this
Next week.
CIE, do you see the dominant contribution to the inverse problem for a long time? Can you suss out what provides the dominant contribution?
No, I think that's your job. Yeah, long time. Yeah, long time. But I try to learn from you and talk with from the activity, because you have been so generous to share the details. And I think the crucial part should be computation on Grassmannian, right? Grassmannian composed, and so Ken, I think the more I think only this So that's to the, yeah. Okay, so if scattering data is trivial, so you don't have this term. So the whole thing is a m plus n by m plus n dimensional linear algebra. Yeah, you just solve that.
Okay.
And make n to be infinity. Now
Thank you. Any further questions? So then let's stop and have some coffee. Thank you, Derchyi.